Okay. Good afternoon, good evening, everyone. So let us start the section number 85 of our seminar. So today we're going to have two excellent speakers, Professor Otared Kavian and Professor Alberto Saldana. And to introduce Professor Otared Kavian, we have Professor Anna Dubova. So Anna, please.
Okay, thank you very much, Diego. So it's a great pleasure and honor for me to present Professor Otared Kavian. He's Emerit Professor of Université de Versailles. His scientific advisor was during his PhD thesis was Chaim Bresis. Otared is a specialist, great specialist in partial differential equations, linear and nonlinear, elliptic and evolution equation. Is widely cited author in the area of partial differential equation. He is a great specialist in inverse problem, and today he will speak about heat semigroup, Sobolev inequality, and regularity theorem for elliptic PDEs. Please, Otared, you can start.
Okay. Thank you very much to all of you for the invitation. It is a great honor for me to speak in front of such egregious colleagues as the organizer and as the participants. So I'm going to talk about some results where the heat semigroup, the Sobolev inequalities, and regularity theorems for linear or nonlinear elliptic PDEs are related in an intricate way. But I should say that the results I'm going to talk about are rather old. So this is rather mathematics for retired professors. But despite this fact, I think there are some interesting parts which can be for the attention of young students. Actually, how should I do to remove? Okay, I don't know how to, because the images are in part of my PDF, so I cannot see what I'm talking. Okay, I see. Yeah, how?
You can pick up with the mouse and move the images, I think. You can move slightly move the images.
But okay. Okay, so that's better. Okay. So I am going to talk about a work which is in progress about regularity theorems for elliptic equations in Lorentz spaces or in Holder spaces. And a great part of the results I'm going to talk about are part of an article which was published in a volume dedicated to the Jairo de Figueiredo about 20 years ago. So it's a pleasure for me to talk about both results because the intricacy between the heat equation and the elliptic equation, I think it's very interesting. Okay, so now I have to go here again. Okay, so to begin with, consider an integer n and greater than 1, and denote by delta the classical Laplacian on Rn. So we know that if we want to solve the heat equation dV over dt minus delta V equals to 0, and V of 0 and x equal an initial date of V0 of x, then in this particular case, using the Fourier transform, one can solve the equation quite easily, and one find that the solution of V is given through a convolution with the heat kernel, which is called G sub t of x, which is this function, this exponential function, okay? So thanks to this explicit, this formula, which gives an explicit relation between V and the initial data, one can see that if we take an exponent P1, which is larger than P0, then the solution V is going to be of class C infinity. In fact, if P0 is less than infinity, it converges also to 0. And we have the estimate, which is norm of V of t in LP1 is less than t to some power, the initial norm in the initial space P0. And this exponent beta, which is n over 2, so n is the dimension, and we have this relation, which is 1 over P0 minus 1 over P1. Okay? So this is thanks to the fact that we have an explicit formula. Now, if we consider an inhomogeneous heat equation, that is the equation dV over dt minus Laplacian of V equals to F, and V of 0 and x equal to an initial date of V0, then in this case, the solution is given by what is called the mild version of the equation, which is V of t equal gt convolution with V0 plus an integral term which takes into account the right-hand side of the equation 4. Okay? But now, what is interesting is that this simple relation can be used in order to show many interesting inequalities, Sobolev inequalities, and also to show regularity results for elliptic equations in a way which is rather elementary. Okay? So consider first the case, so the question is now, we have an equation which is minus Laplacian of u equals to f. We know that f is in some space LQ, for instance, in L1 or L2 or something. And the question is, can we deduce from the equation whether u belongs to a better space, a more regular space? For instance, is u in LR for R larger than P, or whether u is a continuous function, and so on. Okay. So now the aim of this talk is to show that all these questions can be answered thanks to this relation, which is here, the equation, the mild version of the heat equation. Okay. Now, so let me see whether I can, how I can, because the images are on the top of my screen. I have a small screen, so I don't know how to hide this part. Okay, so maybe, okay, maybe I can do this. Okay, so I found a way. Fine, thank you. Okay, so okay, so what did I? Yes, this, we are here. So the elementary remark is the following. We will have a function u which satisfies minus Laplacian of u equals to f. And if we consider that this is, instead of being a stationary equation, is an evolution equation, Then consider the initial date of V0 equals to U, and capital F of t and x equals to f of x, so it's independent of time. And the equation 7 is the evolution equation. But since U is the solution to the stationary equation, of course, V is going to be equal to U for all time, okay? But since we had the relationship V equals given by a convolution plus an integral term, therefore, we can deduce that we have a relation which says that U can be written as GT convolution with U plus an integral term which is 0 to t, integral from 0 to t of GT minus tau convolution with F, okay? So this is a representation formula for any function. You can take, for instance, U, a function which is C infinity with compact support. It doesn't matter. You can take whatever you want. And then by regularization, you can deduce that this relation is true also for other functions, okay? But the interesting point is that we can write the function U as two terms. One term is a smooth function, GT convolution with U, and another term, which is an integral term where the Laplacian of U is used, okay? But since we have t, which can be any positive number, this can be used in an interesting way, okay? For instance, take this in this relation U equals to GT convolution with U with plus the integral term. We take the norm of U in some space LR, okay? So let me, oops, what do I do? I don't know. Okay. So we take R larger than P, and we take the norms of the identity in this space LR. So the first term is norm of U in LR. Then we have the norm of GT convolution with U, which gives us this term. So there is a t to the power something plus an integral term from zero to t of this thing, okay? Now, if it happens that the number Q, that is the space where the Laplacian of U resides, is larger than n over 2, here we can take R equals to infinity, and therefore this means that the norm of U in an infinity is less than something t to the power minus n over 2p plus t to the power 1 minus n over 2q. So we have a t to some negative power here, t to some power which is positive, norm of f in LQ. Okay? So this is regularity results. This means that if the Laplacian of U belongs to LQ and Q is larger than n over 2, then U belongs to L infinity. In fact, if one is a little bit more careful, one can see that, in fact, this term gives that U is in C0 continuous, which goes to infinity of Rn. Because this integral from 0 to t is the limit from the integral of 0 to t minus epsilon, as epsilon goes to 0, in the sense of L infinity. But now, if epsilon is 0 between 0 and t, and tau is between 0 and t minus epsilon, this term, the convolution term, belongs to C0, okay? Because we saw that, in fact, this function is a C infinity function, this function, okay? Therefore, as we take the integral of this term from 0 to t minus epsilon, this term belongs to C0 of Rn, okay? In fact, it belongs to to many other spaces, but what we are interested in here is the continuity. Okay. So now, as epsilon goes to 0, we have convergence in L infinity. Therefore, the result, the integral between 0 and t of gt minus tau convolution with f belongs to C0 of Ra. Okay. There is another interpretation of this inequality which prove easily, is that since f is equal to minus Laplacian of u, we have norm of u in L infinity less than t to the power minus n over 2p, norm of u in LP plus C0 t to this power norm of Laplacian of u in LQ. Okay? So this inequality is true for all t positive. On the left-hand side, we don't have t, and on the right-hand side, we have t. Therefore, we can take the minimum of the right-hand side for t between 0 and infinity, and by taking the minimum, we find that norm of u in L infinity is less than some constant independent of u. Norm of u in LP to the power 1 minus theta, norm of delta u in LQ to the power theta, where theta is this number. And since we are assuming that 2q minus n is strictly positive, this means that theta is actually less than 1, strictly less than 1. Okay? So you see this, this point of view tells us that whenever we can study this term, integral from 0 to t of this term, gt minus tau convolution with f, in some other functional space, for instance, a Lorentz space or the space of Holder continuous function or any other space, then we can establish some results regarding the function u, which is the solution of minus Laplacian of u equals to f. Okay. So the only thing we have used here is the property that the heat semigroup is mapping some LP0 space to some other space LP1 with a dependence in t, which is t to the power minus something. Okay. And in fact, here is another illustration of the fact that we can use this relation in many ways. Remember that when we have the convolution of this function gt minus tau convolution with Laplacian of u, this can be written also as the gradient of gt minus tau convolution with gradient of u. Okay, because gt minus tau is just exponential, so it is infinity and converges to 0 at infinity. So we can take the derivative in the way we want. And since f is equal to minus Laplacian of u, so we have another representation formula for u, which is u equals to gt convolution with u minus integral of this, this part. Okay. Now, again, assume that now gradient of u belongs to LQ and u belongs to LP. So we can take the norm of the relation 10 when R is greater than maximum of P and Q, and we have the relation which is here, the relation 11, which says that the norm of U in LR is less than T to some power negative plus the integral of this stuff. Again, here you see that if the exponent of T minus tau is less than 1, this negative exponent is greater than minus 1, actually, then in this case, we can integrate this, this integral and obtain that another result. So first assume that Q is less than between 1 and n. So we know that the space D1Q, which is defined as being the closure of function with C infinity with compact support with respect to the norm of gradient of U, then this space is contained in the space LQ star, which is where Q star is the Sobolev exponent, which is defined as being 1 over Q star equals to 1 over Q minus N. But now, okay, it doesn't, okay, it's here, no. Oh, it's here, okay. No. Yes. But now you see here, we have this relation 11, but now let us look what happens if Q is greater than N, okay? In this case, maybe some of you know that Jacques Lullions and Jacques Denis have proved that when Q is larger than N, the space D1Q is not a subspace of the space of distributions. This means that, of course, we can define the space D1Q in the same way. It is the closure of the smooth function with respect to the norm of gradient of U in LQ. But now, the closure of this function is not even a distribution, it's something else, okay? Despite this fact, the relation we just established allows us to show that when we know that U is in C infinity with compact support, Q is larger than N, and R equals to infinity. Then, okay, oh, it doesn't, oh, you see here, we have this relation and we have this. So in this relation 11, we can take R equals to infinity and Q is larger than N. Therefore, norm of U in L infinity is less than this constant plus another constant T to the power 1 over 2 minus N over 2Q. Okay, so this is positive, this exponent is positive because we are assuming that Q is larger than N. And now, if we take the closure of C infinity function with compact support with respect to the norm of gradient U in LQ and the norm of U in LP, this means that if we take the space LP intersected with D1Q, then this space is contained in C0 of Rn, okay? So the space D1Q of Rn is not a subspace of distribution, but its intersection with any LP space is contained in the space of continuous function which go to 0 at infinity, okay? So again, this is only is established using only the fact that the heat semigroup maps some LP space to some other LP space, okay? And moreover, we again by minimizing the, okay, I don't know, where is it? Okay, it doesn't work, I don't know why. It's here. No, it's not here. Okay, by minimizing the inequality we had with respect to the number T, we show that when Q is larger than N, we have a sort of Gallardo-Nirenberg inequality, but this inequality cannot be obtained by interpolation because all the interpolation we can do are between spaces of functions, but the space of the closure of smooth function with respect to the norm of gradient to LMQ is not a space of functions. Therefore, this inequality cannot be proved by using interpolation of functional spaces. Okay. Now, the remainder of this talk, I'm going to show first a relationship between some inequalities, and then show how one can use the representation formula in order to show, to establish some regularity results. Okay, so now consider the following. Consider that omega is a domain of Rn, and we consider a second order differential operator such that the mapping U maps to LU scalar U is positive. Okay. For instance, you can consider LU equals to minus Laplacian of U with the domain of L equals to this, or more generally, one can consider an elliptic differential operator, which is in the divergence form, but with discontinuous coefficients, etc. Okay. Now, consider the following three inequalities. The first one is the Nash inequality, which says that the norm of phi in L2 to some power is less than norm of phi in L1 to some power, L phi scalar phi. Okay, so here D is a number, okay, any number. So this is a certain inequality. Next, consider what is called the ultra contractivity of a semigroup. So let S of t being the semigroup generated by L, which is exponential of minus TL, and assume that if U0 belongs to domain of L and in L1, then S of t U0 belongs to L2 with a norm which is like a constant t to the power minus d over 4 for some exponent d positive. Okay, so this is a second category of inequalities. And the third category is, consider that there is a constant C3 and a finite exponent 2 star. Here I put a star, substar, okay, larger than 2, such that for all phi in D of L, we have norm of phi in L2 star less than C3 L phi phi. Okay, remember that if you take the operator L to be minus Laplacian, the first inequality is the classical Nash inequality where you take D equals to N. The third inequality, ultra contractivity for the Laplacian, here, as we saw, is D equals to N also. And the Sobolev inequality, 2 star, is 2N over N minus 2, where N is larger or equal than 3. Okay? But now, there has been many works, so I cite here a few of them. So the first one is the result by Fukushima, and in fact, Philippe Benillan had used such a property for the study of a nonlinear equation. But Fukushima, then Varopoulos, then Phelps and Strouk, and after them, many people have studied the fact that these inequalities are essentially equivalent. This means that if you can establish Nash inequality for an operator L, you can conclude that you have a sort of Sobolev inequality, and you have the fact that the heat semigroup maps L1 in L2. Okay. So the first result I'm going to prove is that Nash inequality and ultracontractivity are equivalent. Okay. So assume that you have a semigroup which acts also in L1. This means that it maps L1 into L1. Okay. And assume that the Nash inequality holds. Nash inequality is this, the fact that norm of phi in L2 is controlled by norm of phi in L1 and L phi phi. Okay. Then the ultracontractivity inequality, which is this inequality for the semigroup, this inequality holds with the same exponent d. Okay. The important thing is that we have the same exponent. If d appears in the Nash inequality, the same d appears in the ultracontractivity inequality. And we have also, in the case that L is self-adjoint, we have the reverse implication. If we have the ultracontractivity inequality, then we have the Nash inequality with the same exponent d. Okay? And here is the result for the equivalence of Nash and Sobolev inequalities. If in the Nash inequality we have d larger than 2, and we have at the same time Nash inequality, then this is equivalent to say that the number 2 star is 2d over d minus 2, and we have the Sobolev inequality. So these two are equivalent. But moreover, we have a little bit more. If it happens that d is equal to 2 in the Nash inequality, we have a sort of Schrödinger inequality. That is the exponential of omega phi squared over L phi phi belongs to L1 log of omega for any omega positive. Okay. And finally, if in the Nash inequality the exponent d is strictly less than 2, then norm of phi in L infinity squared is less than constant and norm of phi in L2 plus CL phi phi. So this means that in this case, the domain of square root of L, if L is self-adjoint, is contained in L infinity. Okay. So because of the lack of time, I'm just going to show you briefly the equivalence of Nash inequality and the ultracontractivity property. And for the remainder, I can give you the PDF of the talk where the results are presented. Okay. So first, some remarks. The exponent d which appears in the inequality is not necessarily an integer, is a number, is a real number. For instance, if you take any alpha larger than minus n, and on the space Rn, you consider the weighted L2 space. So, which is this space, okay? The integral of x to the power alpha f of x squared dx is finite, okay? Here it lacks, this is finite. So this is the square of the norm, okay? And you consider Lu a sort of Laplacian associated to this weighted space. So this is then the Nash inequality holds with the number d equals to alpha plus n. Okay, so the Sobolev inequality, the ultracontractivity, everything holds, but with the number d being alpha plus n. Okay, so it can be anything, in fact. The exponent d is a sort of a dimension for the underlying Hilbert space, in fact. And there are many people who have studied these inequalities in terms of geometric properties of the space of manifolds. This means that the ball of radius r has a volume, a measure of order constant times r to the power d. Okay, as one can see, for instance, for the distance, for in this case, with the weighted L2 space, if you take this measure, the volume of the ball center at 0 increases like r to the power alpha plus n. Okay? Well, in the case of the Euclidean space, in fact, and taking L equals to minus delta, all the inequalities, Nash inequality, Sobolev inequality, etc., can be obtained, in fact, through a geometric property, which is called the Brun-Minkowski inequality, which is written here. Okay, but we are not going to study in that. So I'm going to show first the. I don't know how much time I have. Can someone tell me?
Yes, you can. How much do you need? 10 minutes?
No, it depends on your patience.
So yes.
No, okay. So maybe I show just the proof in one sense, and
yes,
then
probably 10 minutes.
Okay, thank you. That's fine. Okay, so assume that the Nash inequality holds, and set beta equals to -4 over d. Okay, then call u of t exponential minus tl. So this is the solution of this equation: dtu equals to minus lu, u of 0 equals to u0. Then consider g of t, the norm of u of t squared. So the derivative is this: g prime of t is minus 2 times lu scalar u. Okay. Now, in relation 12, we have that L phi phi is larger than something. Okay, larger than norm of phi in L2 to some power divided by C1 norm of phi in L1 to some power. Okay, so we are going to use this inequality. Okay, and this implies that minus g prime of t is equal to 2 times LUU. So it is larger than 2 times what I just mentioned, which is this this quantity. Okay, so this is the norm in L2, and this is the norm in L1 to the negative power. Okay, but we assume also that the norm of u in L1 is comparable to the norm of u0 in L1. So we can say that this is a lower bound for this is c times norm of u0 in L1 to the power minus beta, and this is just g of t to the power 2 plus beta over 2. Okay, so now this inequality, this is a differential inequality, can be written as g of t to the power minus beta over 2 prime bigger than a constant times norm of u0 in L1 to the power minus beta. Okay, therefore, if we take the integral of this, we obtain that g of t to the power minus beta over 2 is larger than this. Now g of 0 is positive, therefore g of t to the power minus beta over 2 is larger than something times t. Okay, therefore, since g of t is just norm of u of t in L2 squared, from this inequality we obtain that norm of u in L2 is less than this this inequality with this quantity. So this is precisely the property that the heat semigroup maps L1 into L2 with a norm of order t to the power minus d over 4. Okay, so this is, you see, it's very elementary. Okay, in this case, you see, we don't need that L to be self-adjoint. Okay, but okay, if we assume that the operator L star also satisfies a Nash inequality, then using the same property, we can conclude that in fact the heat semigroup maps L1 into L infinity with a norm which is of order of t to the power minus d over 4. Okay, so this is the way we write, for instance, for the heat equation in Rn. Usually it is written in this way. Okay. Now another observation is that the Nash inequality is easy to prove, because if we assume that LUU is larger than alpha 0 gradient squared, then using Fourier transform, we know that norm of U in L2 is equal to norm of Fourier transform of U in L2. So this is written in this way. And by splitting the norm of U hat into two parts, where psi is less than 1 and where psi is larger than 1, we obtain this, this inequality. And from this, by a change of scale, we obtain the classical writing of Nash inequality. Okay, so this is the way one can write, because we know that LUU is is larger than a constant norm of gradient of U squared. Okay, so now I would like to, because of the lack of time, I want just to present how to obtain regularity results for elliptic equation with discontinuous coefficients. Okay, so assume that you have an operator L, which is written in this way. So B and C are vectors which satisfy, they are in Ln plus L infinity, and V0 is a function which is in L1, and V0 is positive. It is not written here, but it's supposed positive here. Okay. Now, assume moreover that divergent of C is less than this, minus divergence of B is less than this. These two conditions are there in order to show that we have a sort of Nash inequality both for L and the operator L star. Okay, and we need also the fact that the heat semigroup maps L1 into L1. So these two conditions are there in order to have the property that the heat semigroup maps L1 into L1. Okay, so this implies that for some constant lambda star, we have this property. And the same thing with L star. I didn't write it here, but the same is true for L star. Okay. Without lack of generality, we can assume that, in fact, LUU is always larger than gamma 0 gradient of U squared, because we are interested in regularity result, not in existence of solutions. Okay. So for this problem, we have that S of t, which is ultra contracted with the same exponent as I mentioned before. And therefore, if we consider the heat equation with the second term on the right, we have this this relation psi of t, which is given by the relation which is in equation 26. Okay. Now again, if U is a solution of LU equals to F, we have a representation formula for U, which is U equals to S of TU plus a term which is integral of 0 to t of s of tau f, and f is Lu. Okay, so again here we have a splitting of u in two terms, a term which is smooth, and a term which depends on the operator L. Okay, so again we can take the norm of both sides in LP1, and we have this. Okay, so now if you assume that f belongs to LQ, and we want to find which P1 we can take here, we have to give a sense into this integral term which is here. Okay, and in order to do that, we recall that when f is in LQ, we have s of tau f P1 in L P1 less than this tau to the power minus beta, with beta which is this number, and therefore from the relation which is here, from this relation, we conclude that we have norm of u in P1 less than t to the power minus gamma, with this gamma here, plus c times t to the power minus 1 beta. Okay, so again here we have the regularity result, or Sobolev inequality if you wish, which says that norm of u in P1 is less than this product, and f, recall, that is Lu. Okay, so we have proved that if Lu belongs to LQ for some q larger than n over 2, then the norm of u in L infinity is less than this quantity. Okay, in fact, one can show again that u is actually continuous, and by studying in a better way the integral of 0 to t of s of tau f. Okay, so now when we want to consider the cases q equals to n over 2 or q less than n over 2, this term should be handled with more care, because you see here we have a where is it? Okay, no, I forgot. Okay, I lost it. Oh yes, it's here. If beta is larger than 1, then we cannot integrate this term. Okay, this is the reason. Okay, now for so I just show the result for the case q equals to n over 2. In this case, there exists a number mu star, such that if mu is between 0 and mu star, if you define this functional, this function g of s, which is exponential of mu s, but you cancel out the first terms of the exponential, in fact. Okay, then we have integral of g of bt of f, which is this integral, which is less than some constant t over n over 2. So this means that in this case, the function u belongs to this space, which is sort of Lorentz space. In fact, the integral of g of this u is finite. Okay, and the proof is quite easy, because we just take two parts. G is integral from 0 to t over alpha of s of tau f d tau, and h is integral of t over alpha to t of the other part. So the sum is the function v, which is bt of f, and we are going to study each term separately. So the function h, since t over alpha is far from 0, we have this this property. Okay, norm of h in L infinity is less than tau to the power -1 norm of n over 2, and this is C1 log of alpha independent of t. Okay, and now for lambda given, we haven't chosen yet alpha. We're going to choose alpha such that if lambda over 2 is equal to C1 log of alpha, then the norm of h is less than lambda over 2. Okay, so we take this to be lambda over 2. Okay, and now we have to consider to control the term integral from 0 to t over alpha of s of tau f. Okay, and in order to do that, we recall that v is equal to g plus h. Okay, and therefore, where the function v is larger than lambda is contained in the part where g is larger than lambda over 2. Okay, and therefore the measure of this part where v is larger than lambda is less than some constant lambda over 2 to the power minus n over 2 norm of g in L n over 2. Okay, and also this part norm of g in Ln2 can be controlled by t times some constant alpha to the power -1, and finally we get that where the function v, which is this function, is larger than lambda, this measure is less than exponential of something. Okay, so it's exponential decreasing. Now we use the fact that the integral of g of v can be written in this way: integral from 0 to infinity of g prime of lambda, measure of v larger than lambda, and by integrating, this means that we have less than t over n over 2. Okay, and as it is known, this result is optimal because if there is a counter example in which minus Laplacian of u is equal to f, f belongs to Ln over 2, but u does not belong to L infinity, and the counter example is log of x. Okay, in the domain. Okay, so this is the case for q equal to n over 2. The case when q is less than n over 2 can be treated in the same way. It's a little bit technical at the end, but the proof uses only the fact that we have this ultracontractivity of the heat semigroup. Okay, so now I think I have used all my time, so I'm not going to continue, but if you have questions, I will be happy to. And if the organizer can distribute the PDF, I will be happy to send the PDF. Okay, so
okay.
I finished.
Okay, thank you very much, Otared, for this very nice talk. So we have a few time for some questions. So are there any questions from the audience? You can use a microphone or also you can use the chat. Please go ahead. Okay, the video audio is open for you, so please go ahead.
I would like to formulate one question. Is possible?
Yes, sure. Please.
Okay. Professor Otared Kavian, I would like to know about the solution when the equation is a stochastic application for radiotherapy, because
Yes.
for radiotherapy or the NEA.
Okay,
Fokker-Plan equation, man, like Fokker-Plan.
No, for the stochastic part, I don't know, but for the Fokker-Planck equation, there are situations in which when the drift force is in some has a certain growth at infinity, then the associated semigroup is also ultra contractive. And when the semigroup is ultra contractive, one can use all these methods. Okay, but for the general case, I don't know. I don't know how to use this technique. So I cannot really answer in either way, whether it's possible or it's not possible. I don't know.
Okay, thank you very much, Dr. Otared Kavian.
Okay, any other questions from the audience? I have a small question, Otared, just a curiosity. Do you need to assume some special regularity for the domain omega for the result?
For H10, no. For H10, there is no. But if you have, because you can do the same thing, for instance, for problems with Neumann boundary conditions, or problems with Fourier boundary conditions. For these, you need assumption on the regularity of the boundary.
Okay.
Yes.
Okay, thank you very much. I don't know if nobody has other questions. Probably we can thank Otared for this very nice talk, and thank you very much for being with us.
Thank you very much. Thank you for your attention.
Okay, thank you, Professor.